Hey everyone, welcome back to Calculus 3. This will be part B of Lecture 9. So we just finished up a few examples where we were given position or velocity or acceleration and asked to identify the others from them. We saw that given position, we can derive velocity and acceleration using differentiation. And the most recent example, we saw that if you're given acceleration, we can derive velocity and position from acceleration using integration. Okay, so now I want to switch gears a little bit and talk about something very specific, which is projectile motion. So this is kind of usually where you will where you will start in a physics course with projectile motion. And so we really do have all of the necessary machinery basically to derive the parametric equations for the path of a projectile. Okay, and so when we talk about a projectile, what do we mean? Well, usually what we mean is you've got some kind of a imagine some kind of a cannon over here, or some kind of a device that shoots something, and it fires some kind of a projectile into the air, right? And then the projectile follows a certain path. Okay. And so what we'll be concerned with is how to model that path using the vector valued functions, derivatives, and acceleration and position and such. So a couple of things that we'll assume here. We'll assume that gravity is the only force acting on the projectile after it's launched. Okay, and so that's obviously a big assumption. Right. There's other things that would be acting on the projectile as well, things like air resistance and, mostly air resistance would be the big one, I guess. But we're going to consider that wind resistance and such to be negligible. We're going to assume that gravity is the only thing acting on it. Okay, and so that gravity would act on the projectile in a straight line. The force of gravity would act on it in a vertical straight line. This force will act on the projectile in a vertical straight line. Right, so basically it's gonna be the force that pulls the projectile back down to the ground. For projectile mass, we would say the force due to gravity could be modeled using F, right? This is the force equals negative mg, and then because it's vertical, we would use the J component there. And so m is the mass of the particle, and g is the gravitational constant, right? And so g here the gravitational constant, and there's typically you would represent it using meters, but so it's going to be 9.8 meters per second squared. If somebody does want kind of the representation in feet, it's about 32 feet per second squared. Okay, so that's basically what that constant is. So that's going to be the only force acting on it. That's going to be the force that brings it back down to Earth. Okay, and so how far it travels is going to be jointly dependent upon the velocity at which it leaves the cannon, and also the angle at which it leaves, at the angle at which it is fired relative to the ground. Okay, the force would be just this constant. The force due to gravity would be this constant quantity here. Okay, so without going too much into the physics of it, we do know, of course, by Newton's second law of motion, that this same force of gravity produces an acceleration. So this same force produces an acceleration, and we'll just call it A equals, it'll be some function of t that satisfies the equation. All right, here's the important part. And the equation is F equals m times the acceleration. Mass times acceleration is the force, right? So then the acceleration of the particle is going to be given by what? Well, the mass times the acceleration, right? This piece here is going to be equal to the piece from above, same force. Okay, and so that's going to be, that's that piece. And so then that implies what? Well, if we divide both sides by the mass, then that means the acceleration will be equal to negative g times the j vector. Okay, so that's the acceleration, and this is what we're going to build everything up off of. We're going to build it all up off of this guy basically using integration, right? So let's go back to the physical scenario here. Okay, make sure we understand the physical scenario, and then we'll derive some of these projectile motion formulas. Okay, so we've got, again, kind of this same picture. So there's going to be some initial velocity given to a particle or projectile, we'll call it. And that velocity is going to have a direction, and that direction is going to have some angle with the horizontal. And once the particles or the projectile is fired, it's going to follow some kind of an arc like this. And our task is we want to be able to figure out, where's the height, what's the peak of this thing, how long does it take to get there, what's the velocity at any time on this trajectory, how far out does it land, all of these kinds of questions we want to be able to model. So a projectile of mass m is launched from an initial position r0 with an initial velocity. Okay, so let's get some of this notation down. A projectile of mass m, okay, is launched from an initial position and we'll call that r of 0, r naught, with an initial velocity, and we'll call that v naught. Okay. All right, so we've got a couple things in here that are important. You got the m, you got the initial position, you got the initial velocity. Important. Okay, so we're going to begin with the acceleration that we just derived. So beginning with acceleration as a function of time equal to this constant, there's going to be negative g times the j vector. Okay, we're going to integrate. Right? So the acceleration is the only acceleration that's operating here will be the acceleration due to gravity, right? And it's constant, right? So the velocity will not be constant, position will obviously not be constant, but the acceleration is constant. It's always pulling down on the particle, right? Okay, and so that's what we're going to start with. And so velocity, we know, is just the integral of acceleration. We can integrate this. Okay, and so that's going to be equal to the integral of negative g times the j vector dt. And so what do we get? We get negative gt times the j vector plus some constant. Okay, and we'll call this c1. We're going to derive a couple of constants here. And we can integrate this further to get the position. All right, so we'll integrate the velocity, and that's going to be the integral of negative g t times j plus c1. Okay, so it's going to look like this. And so when we integrate that, what do we get? Make this up a little bit here. Well, this first part becomes negative 1/2 g t squared times j. Okay, and then this is a constant vector, so it'll just be plus c1 times t, and then plus c2, right? There's going to be some additional constant introduced here. Okay, and we can use some of the facts that we've gathered up to this point to kind of figure out what these constants are. So we can use the facts that the initial velocity, v of 0 is equal to v0. Okay, we can use that, and that the initial position at 0 is equal to r of 0. Okay, we can use those two facts basically. Okay, and so v of 0 is equal to v0, right? This is a constant, this is the function evaluated at 0. So that's going to be equal to negative g times t, right? So I'm just going back to this guy here. Negative g times t, in this case is 0, times j plus c1. Okay, so that means c1, which is a vector, it must be v0. Okay, so that part's straightforward. And now we can use this piece in conjunction with this piece to figure out what c2 is. And so r of 0 we know is equal to r naught, which must be equal to negative 1/2 times g, and then t is 0. Right, I'm plugging into this thing here. Okay, and that's times the j vector, plus c1, which we just found to be v naught, times t, right, which would be 0. Right, c1 times t, which is v naught times t, and finally plus c2, which is the last thing, and that's going to be equal to r naught, and so that implies that c2, so these are 0, right, 0, 0, so c2 equals r naught. Okay, so the position vector, right, the position vector valued function is r of t equals negative 1/2 g t squared, so I'm going to put that in parentheses, and that's times j, plus t times v naught plus r naught. Okay, so you got some function here. So this coordinate just basically gets plugged into the j coordinate, and then you add these constant values of v naught and r naught. Well, v naught's not constant, but it's a vector times t, uniformly times t, and then r naught is a constant vector. And you would add all of those together to get the position. Okay, what this is gonna describe is for any time t, where are we in the coordinate system with regard to this path. Okay. All right, so that's the first big piece. That's the main big piece, actually, and the rest of it comes pretty quickly afterwards. Okay. And so oftentimes we don't know r naught and v naught explicitly. Let's write this down. So we do not always know r naught and v naught explicitly. In fact, when you take physics, a big part of making these problems more complicated is, not giving you r naught and v naught explicitly and asking you to find them or derive them in some other way. We may be given a height and an initial speed and an angle. That's more likely what you have. So we may be given an initial height, right, for the position, an initial speed, v naught. Now notice it's not a vector, just the norm of the vector, and an angle basically an angle theta at which the projectile is launched. Okay. So because this is pretty typical, like there's a nice little schematic we can work out to kind of help aid us with these problems, right? And so the following is useful, I'll just say. Okay, the following is useful. Okay, so imagine a coordinate system here. Okay, now your particle is maybe starts here, right? It's the height of the apparatus. Okay, and so you're going to have some initial height given, right? And that's going to correspond with your R naught. Okay, and the initial speed will be, you know, basically the magnitude of the vector that's that represents the initial velocity. That initial speed, it can be broken down. So you've got some angle theta, which basically the angle at which the projectile is launched. It's going to make some angle with the horizontal theta. This would be like your v naught. Okay. And so you can see what's going to happen here. This will get launched, and then gravity will start to take over and start to pull it back down to Earth. Okay. And so what is this? Well, this is going to be the xi piece of the velocity, and this would be the yj piece of the velocity. Okay. And so kind of the way to make sense of all this would be to say that your initial velocity is equal to xi plus yj. Okay. And what is that? Well, xi, well, that's going to be the magnitude of the velocity times the cosine of whatever this angle theta is, right? That's the cosine is the horizontal. So it'll be the magnitude of the velocity, namely the speed, times cosine of theta, right? And that's going to be the I component of velocity. And what about the yj? Well, what's that piece? Well, it's similarly, it's going to be the magnitude of the velocity, like the speed again, times the sine of theta, times the j vector. And that's going to give you that piece of velocity. Okay, so if you're just told the magnitude of velocity and the angle theta, you can derive the velocity vector value function really quickly using this kind of a technique, right? This would all simplify down to basically v naught, the speed, times cos theta times I, plus the speed times sine theta times j. Okay, and so we can use this to rewrite the position vector. Rewrite the position vector. So r of t, right, we just saw that it's negative 1/2 gt squared times j plus t times v naught plus r naught. Right, so that's kind of what we started with. And now what we can do is we can, given v naught and r naught are not told to us explicitly most of the time, we can rewrite this as negative 1/2 gt squared times j plus, now instead of v naught, let's plug all this in. Okay, so v naught, plus t times j. So it would be plus t times, and then it'll be v naught cos theta I plus t times v naught sine theta times j. Okay, and then plus, what is r? R is just going to be h, right? h of j. Okay. Okay. Okay, so that piece I kind of omitted, but you can see that now, right? So h is just the height that's initially given to you. R0 is the initial position, and so the initial position is 0 on the x-axis and h on the y-axis, so that's why it's h times j. Okay, and then we can combine some of this up to make it a little more straightforward here. So for the I vector, we now have an I component here, right? So we've got v0 cos theta times I plus, and then it's going to be h plus v0 sine theta times t minus 1/2 gt squared, and that's times j. Okay. Okie dokie. All right, so this is a slightly nicer way to deal with this in the cases where you're not explicitly told the initial velocity vector and the initial position vector. Usually you're given h and theta instead, and maybe a speed. And from that you can quickly deduce sort of these things, but you know. Okay. All right. Let's see here. Okay, so let's do an example. Let's do an example. Just a quick example, kind of using some of these. It won't be too quick, it'll take a second to write it down here. A baseball is hit 3 feet above ground level at 100 feet per second. I have no idea if that's realistic or not, but that's the problem. So a baseball is hit 3 feet above ground level at 100 feet per second and at an angle of 45 degrees. With the ground. Okay. Find the maximum height reached by the baseball. Find the max height reached by the baseball. And the question is also, will it clear a 10-foot high fence located 300 feet from home plate? Okay. All right, so that's the question. A baseball is hit 3 feet above ground level at 100 feet per second and at an angle of 45 degrees with the ground. We want to know two things. First, we want to find the maximum height reached by the baseball. Secondarily, we want to know if the baseball, given this initial information, if the baseball will clear a 10-foot high fence that is located 300 feet from home plate. Okay. All right, so we're given a bunch of information here. So what do we have? We've got h equals 3. Okay, we're told it's 3 feet above ground level. We're given v0. We're told it's 100 feet per second. So you can leave the units on here. And we're told theta is 45 degrees. Okay. All right, so we can kind of draw a picture here just to make sure this is kind of clear. Okay, so this is where the ball is hit. So it starts at 3. H equals 3. It takes off, and this angle theta is 45 degrees with the horizontal. Okay. And we're told that, 300 feet out here, so 300 feet, there's a 10-foot high fence. Okay. Now, two things we're interested in is, first of all, what's the max height here? And then second of all, what happens out here? Can it clear this after 300 feet. Basically, this one will figure out one way, this one will figure out another way. This one, well, this one is probably, we'll start with this one. We'll start with identifying the maximum height. Okay, but first let's actually plug everything into the velocity, or into the position vector, and see what we have here. So r of t is equal to, I'm just kind of going to plug everything in here. We're going to get 100 times the cosine of pi over 4, which is 45 degrees, times t times I, plus 3 plus, that's the initial height, is 3 plus 100 sine of pi over 4 t, and then minus 16t squared. And that's all the j component. Okay. All right, let's simplify this a bit. So this would be 50, and then cosine of pi over, well, cosine of pi over 4 is square root of 2 over 2, so 100 divided by 2 is 50, and then this will be 50 times the square root of 2, basically, times t times I. And then what is this all over here? Well, this is 3 plus, and then this is the same thing, 50 times the square root of 2 times t, and then minus 16t squared, and that's all times j. All right. And so that's the position. What about the velocity? Well, the velocity is the derivative, right? And so the derivative here would be just 50 times the square root of 2 times I, plus, now this one's going to 0. This one will be 50 times the square root of 2, and then this one will be minus 32t. Okay, so we got that one. So we got those two pieces. Okay, now how do we figure out this maximum height question, right? So the maximum height, when is that going to happen? Well, conceptually, I mean, you kind of think of it like you have to always think about what's going on with the velocity and what's going on with the position at various times that are important, right? The maximum height, the velocity of the y component will be exactly 0, right? It'll go up for a while and have a positive velocity, and then it'll stop and it'll come back down, right? So we want to know precisely when this is 0. So the maximum height will occur when the velocity of the j component is 0. Okay. Right, so relatively straightforward there, right? We can just plug in this piece here and set it equal to 0, right? So we want to know when 50 times the square root of 2 minus 32t equals 0. At what time? Right? So basically 50 square root of 2 equals 32t, and t is equal to 50 times the square root of 2 over 32, which is 25 times the square root of 2 over 16. And we can just plug that in and figure out, you know, what does that look like, actual like decimal number, 2.21 seconds. Okay, so the ball is hit, 2.2 seconds later, it's at its maximum height. Okay, we could obviously figure out what its maximum height is by plugging in 2.21 into this, and the j component in particular would tell us what that max height is. Okay, all right, so we've got part 1 sorted. What about part 2? So what will happen to the baseball when it's 300 feet home from plate? 300 feet from home plate. What will be the baseball's position when it is 300 feet, my goodness, 300 feet from home plate. What will its position be? How high off the ground will it be? Namely, will it be more than 10 feet off the ground? Because if it is, it's going over that fence. If it's not, it's going to hit that fence. Okay, so first of all, we need to figure out at what time will the ball be 300 feet from home plate. And so that's going to be, so we first need to set the x component of r of t equal to 300 feet. Okay, we start with that, right? So that means we say 50 times the square root of 2 times t is equal to 300, right? I just pulled this right off of the x component of the position vector. So that means t would be 300 divided by 50 times the square root of 2. Okay, and so that is going to be 3 times the square root of 2, approximately 4.24 seconds. Okay, and so that's not the answer. Obviously, that just tells us what value to plug into the position function. So at t equals 4.24 seconds, the height of the baseball is, well, basically just have to plug in y of t, don't we? So it'll be y of 4.24. And that's equal to 3 plus 50 times the square root of 2 times 3 square root of 2. I'm kind of using this value up here. And then minus 16 times 3 square root of 2 squared. Okay, and so we can figure out all of this pretty quickly. That'd be 3 plus 50 times 2 times 3 minus, and this will be 16 times 9 times 2. Everything is squared and square roots. So, okay, so that's going to be 3 plus 300 minus, now this one is a little harder to figure out, it's 288. Okay, and so what do we get? Well, it's 303 minus 288, which we can see is 15 feet. Okay, so again, I kind of went through that quickly, but it's just arithmetic, really. So, and so when the, so we've got this fence out here, and this ball that gets shot by a baseball, and it's going to just clear that fence. If the fence is 10 feet high, the ball will be 15 feet high when it hits that distance from home plate. So that means it's going over the fence, right? The ball will go over the fence. Okay. All right. Perfect. So that was a very nice example. Now, obviously, there are tons and tons of different examples that you can come up with. Pick up any book, any Calc 3 book or physics book at this point, and you should be able to do most of the problems just with knowing this handful of you're not going to do most of the problems in a physics book, but this is the starting point for for basically for dynamics in physics, understanding kinematics in physics. Okay, so excellent. We'll leave it at that, and when we come back next time, we'll talk about tangent vectors and normal vectors, and we'll get back into kind of understanding some of the complexities of 3D calculus. All right, we'll see you all then. Take care.